Okay, this is a solution to homework problem number 1334. The problem says that there are two infinitely long parallel plates that both have a width of W. So this is radiation problem 13-34, and we're looking at infinitely long plates of width W. And they are offset from one another. Okay. And they are separated also by W, and they are offset by W. Okay? So we're told that plate 1 has area A1 and is held at a temperature of T1 equals 700 Kelvin. And area A2 has a temperature T2, which is equal to 300 Kelvin. And the problem asks us to try and find the heat transfer rate due to radiation between these two surfaces. So the Q dot from 1 to 2 is what we're after. Okay? So from our radiation class, we know that Q dot from 1 to 2 is going to equal the area A1 times the view factor F12 times the Stefan-Boltzmann constant times T1 to the fourth minus T2 to the fourth. Okay. So, quick little change here. It's not asking for the heat transfer rate, but we're asked to find the heat flux. So we want to find little q dot from 1 to 2, which of course is just equal to Q dot 1, 2 divided by the area, right, A1. Okay, so we go back to our equation for big Q, and we see that we're going to get rid of the A1, so we'll have little q dot from 1 to 2 is just going to equal the view factor from 1 to 2 times sigma times T1 to the 4 minus T2 to the 4. So we're given T1 and T2. We know our Stefan-Boltzmann constant of 5.67 times 10 to the minus 8. And we only need to try and calculate what F12 is. Okay. So how do we do that? Well, this problem, we're told we have infinitely long surfaces. So infinite long surfaces. So anytime we have an infinitely long surface, we're allowed to use a technique called the cross strings method. And the cross strings method says the view factor from I to j is equal to the sum of all the crossed strings minus the sum of the uncrossed. Okay? Divided by 2 times the string on surface I. Okay. So let's go ahead and let's try and draw in all of our different strings. So we're going to first locate all of our vertices. 1, 2, 3, and 4. And we will just draw lines that connect all of them. I'm going to show these dashed lines. So this first string we'll call L1. Then over here we have another string called L2. then we notice that I drew a string previously here that connects this vertex to this one, and we are going to call that L4. And lastly, we have a string that goes from here to here, and this will be L3. Okay. We can go ahead and connect a vertex, a string from here to here, and we can call that L5. And if we wanted to, even though we won't need it, here we'll have L6. So just by looking at it, we know that L5 is equal to W. Okay, so let's go back to our equation here. We see that f from 1 to 2 is then going to equal the sum of the cross strings, which are L3 and L4, you subtract from that the sum of all of the uncrossed strings. So the uncrossed strings are L1 and L2. And we divide from that 2 times the string that's on surface 1. So L5. 2 times L5. Okay. So what we're going to need to do is just find all of these different lengths. So we need to find the lengths of all the strings. So let's go ahead and start. Just due to geometry, L1 is going to equal the sum, the square root of the sum of the squares, and that is W squared plus W squared. So let's quickly go back and look at what that is. L1, so we can draw this put a triangle in here, right? It's a right triangle, and we know that the hypotenuse, or L1, is just going to equal to the square root of the sum of the squares, where this distance is W, and this distance here is also W. Okay. So this is just going to equal the square root of 2 times W. We do the same thing for L2, and that's going to again just equal W squared, the square root of W squared plus W squared, which is equal to the square root of 2 times W. L3 is going to equal the square root of W squared plus 2 times W squared, and this is going to equal the square root of 5 times W. Then we have L4, which is just equal to W, and L5, which also is just equal to W. Okay, so now that we have all the lengths of all the strings, we can go back to our formula. We have F12 is going to equal, plugging in for L3, we have square root of 5 times W, plus the length of L4, which is just W, minus the length of string L1, which is the square root of 2 times W, plus string 2, which is also square root of 2 times W, divided by 2 times string L5, which you said is just equal to W. So if we do this, we'll notice that we can factor out a W from the top, and we have a W on the bottom, so all our W's will cancel. And we will be left with F12 is equal to 0.2038. Okay. So now that we have F12, we can go back to our equation that our heat flux from 1 to 2 is just equal to the view factor from 1 to 2 times the Stefan-Boltzmann constant times T1 to the 4th minus T2 to the 4th. Plug in values. F12 is 0.2038. Stefan-Boltzmann 5.67 times 10 to the minus 8. Then we have the temperature T1 was given to us as 700 Kelvin raised to the 4 minus T2, which is 300 Kelvin raised to the 4. And we will find that our heat flux is equal to 2,680 watts per meter squared. And that is the solution for homework problem 1334.